Going for the last topic of this session, polynomial shape function using coordinate system. Same, but it is for rectangular element that we are going to see now. What we seen were 2D bar. The second we seen 2D beam. Then we seen triangular element in which three nodes were there. And here now we are going to see for rectangular element. Now if I go for rectangular element, then first of all we have to see how that rectangle we are going to consider here. Now you can see in the PPT that I'm showing the rectangle under analysis, and that rectangle is in global coordinate system, right? Or even you can say it as a local coordinate system also if it is for this element only. So there are four corners that we have, and all that four corners are actually representing the nodes. Therefore, there will be four nodes: node 1, node 2, node 3, and node 4. Each node is going to have two possibilities of displacement, either in x direction, which we are going to call as u, or in y direction, which we are going to call as a v. So therefore, if I go for the displacement of node 1, node 2, node 3, and node 4, then they are going to be u1, u2, u3, and u4 in x direction, and v1, v2, v3, and v4 in y direction. Okay. Now, if we see any point inside the element P which is having displacement u and v in x and y directions. So actually using shape functions, we are going to find out the properties, behavior, or any other parameter of this P point or any generalized point inside the element. Here, the coordinates for 1, 2, 3, and 4 are x1, y1, x2, y2, x3, y3, and x4, y4 respectively. So this is a global coordinate system which we have to convert or we have to consider in uh, natural coordinate system also. As we know that the center of that is going to be considered as a reference, whereas zeta and eta are the two displacements directions. Whereas there is one more point inside whose coordinates are zeta and eta actually. Whereas four nodes that we are considering here for rectangular element, that are one, node 2, node 3, and node 4. For that four nodes, we have coordinates -1, -1, 1, -1, 1, 1, and -1, 1 for zeta and eta. So if you see node 1, I am just revising this again. Okay. Actually, I discussed this in detail in the previous session also when I was discussing for triangular element. Here also I am revising that again so that hammering that again and again on you may make you to remember that or to understand that. So in node 1 in bracket, if you can see two values, that two values -1, -1 are actually representing zeta, first value zeta, that is this zeta, x direction, and this second value eta. So the value of zeta and eta for one is -1 and -1. You can consider this center line and this vertical center line as the references, and you can consider the values right to the vertical are positive, left to the vertical are negative for zeta. You can see zeta is negative for 4 and 1 and positive for 3 and 2. Similarly, you can consider a horizontal line from center. The values above that horizontal line for eta are positive, and values below that center line, horizontal center line, is negative. Then you can see that for 1 and 2, eta is -1, for 4 and 3, eta is 1, 1. Anyway, so this is the basic information, basic consideration you can see that is required for further analysis. What is that further analysis that we'll see? So as I told you about what is x1, y1, x2, y2, x3, y3, x4, y4, and -1, -1, 1, -1, 1, 1, and 1, -1, 1. Whereas x and y for p and zeta and eta for p in natural coordinates, these all actually, as I explained, is written here also, so that in future when you will have a printout of these PPTs, that will be known to you. Now I'll go for the shape function for linear strain rectangular element. So you just uh, concentrate on this words terminology. What is that? Linear strain rectangular element. It is called as LSR. Huh? Before to this, I think in triangle we use CSP, constant strain triangle. Here we are linear strain rectangle or rectangular. So LSR element is also a word used for this rectangular element, or short form LSR is used. So you just careful for that LSR. Now I'll go for the shape function of that. But before shape function, the information that we have for this element, we will tabulate that so that it can be used for creation of shape function. What is that information? So this information is tabulated in this particular table, in where you can see you just concentrate on this particular table and the values given in that table. So you can see that the first column is nodes. So there are 4 nodes: node 1, node 2, node 3, and node 4. These 4 nodes, as you can see in the diagram. And we are going to have 4 shape functions also. In the previous case also, in the previous sessions also, I explained that shape functions actually depends on number of nodes. If it is 4 nodes, there will be 4 shape functions, 2 nodes, 2 shape functions, 3 nodes, 3 shape functions, and so on. So here, therefore, we are going to have 4 shape functions: n1, n2, n3, and n4. Right? And the last column is about natural coordinates. So in natural coordinates, we are having zeta and eta 2 directions, and whatever the coordinates we use for node 1, as you can see, -1, -1, that is written here, -1, -1. For node 2, coordinates of that, node 3, coordinates of that, node 4, coordinates of that. No doubt. So these last 2 columns are clear. Now let us go for these values. What are these values written here for n1, n2, n3, and 4? Now, in the previous case also, as we discussed already, that uh, we actually consider, or the property of shape function is, if the shape function is 1 at one node, then it is 0 at the other all nodes, right? So this was the property we discussed actually for the shape functions. So here you can see that for node 1, n1 is 1, whereas n2, n3, n4 is 0. It must be 0 because we just give displacement to one node only for one shape functions. Then displacement to and displacement of all other node is 0. And in this way, the analysis. Uh, so the second is Second case is node 2, where n2 is 1 on and all other nodes, shape functions, sorry, all other shape functions are 0. Or in other word, displacement is 1 and all other are having 0 displacement. 3, node 3, n3 is 1, all other 0, and node 4, n4 is 1 and all other 0. Right? So you understood this table actually, what are the values that are written there. So we'll use this table as a reference and we'll go for creation of shape functions now for this rectangular body. So as I said that in semester examination, till date, this derivation and all is not asked for triangular or rectangular. That was asked for two case only, two bar only, not even beam, because in beam also you are having four coordinates. Anyway, but still you learn that and be prepared for that, because the numerical problems are going to be faced on the basis of this concept in the coming units, maybe in unit 3, 4, 5, depends what concept will be there in which unit. So you just understand these basic fundamentals also. Let us go for derivation. So polynomial equation of shape function for linear strain rectangular element is given by this equation. So it is similar to that xy equation, just the x is replaced by zeta and y is replaced by eta. So in this way, the polynomial equation can be written like this. So this is generalized form of this polynomial equation, and this n then after can be replaced as n1, n2, n3, n4 for corresponding shape functions. Now if I go for first case, if I go for n1, then the shape function is going to be like this, which is going to be same, no doubt. It is a0, a1, a2, and a3, which we used as a alpha also in previous cases. Huh? So you can use alpha also, a0, a1, a2, a3 constants, and zeta and eta. There are two displacements in the natural coordinates in that particular directions. So if n1 is this, we have this equation, then I can go for finding the value of n1, right? Value of n1 at four nodes. At four nodes. How? Like this. At node 1, n1 is 1. You can see here. n1 is 1. And a1 as it is, but the value of zeta for node 1, can you see first row, node 1, value of zeta is -1 and value of eta is -1. So I'm going to put the value of zeta -1, eta -1, here zeta and eta both -1, and I will reach to this equation that 1 is equal to a0 minus a1 minus a2 plus a3. So you just put this corresponding values and you will reach to this equation. Now I'll go for at node 2. At node 2, value of n1 is 0. You can see here 0. Therefore 0 here. Whereas the value of zeta 1 and eta -1, these two values, if used in this equation, then the equation comes out to be this. 0 is equal to a0 plus a1 minus a2 minus a3. Similarly, I can do that for node 3 also, where n1 value is 0 and zeta and eta value are 1 and 1, which gives me 0 is equal to a0 plus a1 plus a2 plus a3 as the equation. And for node 4, it gives 0 is equal to A0 minus A1 plus A2 minus A3. So these are the four relations we have received of A1, A2, A0, A1, A2, A3. So our target is to find out the values of this A0, A1, A2 and A3, which after found can be written here in this equation, A0, A1, A2, A3, and therefore I will get the value or the equation of N1, that is shape function 1, in terms of zeta and eta only, right? So if zeta and eta or any zeta is known, eta can be calculated. If eta is known, zeta can be calculated. So I am interested in finding the values of constants A1, A0, A1, A2, A3. Now we have four equations and four unknowns. We have four equations and four unknowns, and therefore it is possible for me to find out the values of all that four constants. Now, you can go for solving this simultaneously, combining each other, and you can find that values of A0, A1, A2, A3. This is the one technique. And other technique, you can use the help or you can take the help of mathematics, and you can ask for the matrices to solve this for you, right? So as I said in previous sessions also, that matrices is one of the tool which is actually used for getting the quick results. So four equations, four unknowns. These four equations can be written in matrix form in this way. So if this matrix is multiplied to this, you will come out with these equations. As this first row can be multiplied to this column, which is equal to 1. So this will be the first result, and so on, right? So this is now converted to matrix form, and my target now is to find out the value of A1, A2, A3, A0. So what to do? So as I said, and saying again and again, and I'll repeat that again and again in the coming sessions also, that you go for revision of matrices, concept of matrices. I'm going to apply now. What is that? First, adding row 4 to row 1 and row 3 to row 2. So this operations are possible in matrices. By doing this type of operation, the ultimate result or the matrices previous to before operations and after operation are same. Values of that remain same. Okay, so we are not actually changing these equations. By doing this, it is okay. Anyway, you go for revision of that matrices and understand what is the basic concept. You just proceed with the steps here. That what is that step? Row 4 to row 1. Add. We have to add. What is row 4? This is row 4. If it is added to row 1, row 1 comes out to be 1 plus 1, 2, minus 1, minus 1, minus 2, right? Then 1, minus 1, 0, minus 1, 1, 0. Similarly, row 3 to row 2. That is, this is 3 row and this is row 4. Row 2. So 3, 1 plus 1, 2, 1 plus 1, 2, 1 minus 1, 0, 1 minus 1, 0. So here 4 zeros you are receiving and 2, 2, 2 minus 2 you are receiving. Actually, the end result is we are actually moving towards diagonal matrix. I don't know whether you remember this term or not. I want a diagonal matrix of 1. Diagonal unit matrix. We want diagonal unit matrix. Or simply unit matrix, just unit matrix is also enough. So I want unit matrix. So I am going to go for that unit matrix. And you learn what is unit matrix. So this is the operation performed. Now this operation, whatever performed here on these two rows, it is applicable to all. So this in this case also it must be changed. But whatever the change will be there, these values are constant values. Get it? So we are going to consider that as a constant only. Here also there will be change. Row 1, row 4 is added to row 1, it remains 1, and row 3 is added to row 2, remains 0. So there is no unchange here in this case, but here we are having change. Next is adding row 2 to 1 and row 4 to row 3. So row 2 if added to row 1, can you see? Row 2, 2 plus 2, 4, 2 minus 2, 0. Here again you are getting 0. You want 0 in all other places except the diagonal. And at the diagonal you want a 1 value. Then only it is going to be unit matrix. And also one more operation, row 4 to row 3. So you are getting these. So I'm not going in detail of that. These PPTs will be available to you. You can cross check that whether it is corrected value is received or not. And then after I'll go for multiplying 0.25. I want this 4 to be 1. So if you multiply 0.25 to 4, you will come out with 1. And if you multiply 0.5 to 2, you will come out with 1. So in this way, these two operations also performed for getting this 1, 1, 1 and minus 1. This will take care of this in the next steps. And you can see here 0.25 is coming here because you are multiplying row 1 with 0.25. Although there is multiplication to row 2 and 3 also, but there is a 0, so there is no change. But adding and all will make this 3 also 0.25 minus 2 point, minus 2.5, and this keys to this particular form. The only remained is minus 1 here and minus 1 here. That is eliminated in the next step by adding row 2 and row 4 in the previous case. We come out with this where minus 1 is only the remain portion we have. So by multiplying minus 1 to row 4 minus row 4, you will come out with positive of 1, and here minus 2 5 will be positive thereafter. So here actually we are receiving the unit matrix. What is the uh, benefit of this unit matrix? You just now go for multiplying this A0, A1, A2, A3 to this first row. You will get the value of A0. It is 0.25. If you multiply this A0, A1, A2, A3 to second row, you will get the value of A1. It is minus 2. For third case, you will get the value of A2, and for fourth case, you will get the value of A3. In this way, as I said, what we were interested that A0, A1, A2, A3 values that are received. So A0 is 1 by 4, that is 0.25. 0.25 is 1 by 4. A1 is minus 0.25, that is minus 1 by 4. A2 is minus 0.25, that is minus 1 by 4, and A3 is 1 by 4, that is 0.25, which is 1 by 4. If I use this A1, A0, A1, A2 and A3 in the general equation of n1 that we were having. So that comes out to be like this. Just putting the value of A0, A1, A2 and A3, keeping zeta and eta as it is, we are coming out to this result. After some mathematical operation on it, you are receiving this, and end you will receive the shape function 1 in terms of zeta and eta. So how these shape functions helps to find out the intermediate values, that you understood already by solving two problems. We solved that problem for two node case only. But now here we are having the shape function for rectangular element, four nodes. Now only one shape function is received, right? And we have four shape functions. So you can go for using the same concepts for N2, N3, N4, and you can receive the value of N2, N3 and N4 also with the help of same methodology. Now you can see here, or you can compare here for any trick that can be used for remembering these four equations, because as I said, you have to go for solving some numerical problems depending on this concept, even though if you don't know or don't remember this derivation how it is derived, but it is necessary to remember this all four equations that you are receiving in case of rectangular element, three equations that you are receiving in case of triangular element, then four, actually three only received which were uh, in duplicate form in case of a beam element, n1, n2, n3, n4, n5, n6. But we are using n1, n2, n3 only because n4, n5, n6 is same. And 2, n1, n2 for bar case. So here if you see the trick, you can find n1 you have both minus eta, and n3 you have both plus. Whereas in case of n2, zeta is minus, n4 eta is minus, and n4 zeta is minus. Second, n2, 2, second term is minus. In terms of n4, first term is minus, whereas n1 is minus and n3 is plus terms.